let me invite Lindsay Kay for the next Tech Talk presentation. Some small challenges. Okay, everything is under control. Thank you for your patience.
Sure thing. Good morning, everybody. My name is Lindsay Kay. I'm a software engineer. Hello? Yeah, I'm a software engineer. I work for Creoox RG. So for the past 10 years, or past 13 years, my specialty has been making graphics middleware for visualizing large engineering models in the browser. And yeah, so I'm gonna my talk's gonna be about some of my experiences doing 3D graphics on the web. And yeah, so starting with the JavaScript in the 90s and 2000s, it was considered not a real programming language. It was really just considered a language for enriching a HTML interface with form validation and user experience. And to code application logic in JavaScript was considered not a best practice. And as a student in the 2000s, my friends and I, one of our sports was to code graphics algorithms in the worst languages possible. So we would try to write things like, ray tracers in I don't know, Prolog or something, or whatever. And so my friend Oliver wrote a ray tracer in JavaScript around 2000, 2001, as a joke. But over the next 13 years, people rewrote it and optimized it and adapted it to using the latest web APIs, and now it's actually really performant. So if you go to that URL, you get a good example of how something that started as a joke actually ended up not a joke. So notice the upgrades on that. I've made way too many slides, so My hobby engine was Scene.js. I wrote this in JavaScript, and it was rendering graphics using HTML divs, which is kind of a ridiculous thing to do, but that was the point. And so it could render, maybe 4 or 5 of these cubes interactively. And I was inspired by VRML and any sort of declarative scene description languages. So that's just another view of the Scene.js idea. But then in 2006, Vladimir Vukovic at Mozilla presented his experimental Canvas 3D to Mozilla management, and they were really impressed with that. And then posted his experiments on his blog. And so here we had the Mozilla actually rendering 3D graphics using the underlying OpenGL ES libraries. And it was very eye-catching to see a rotating shaded cube actually in the browser. It was a really strange thing to see. And so I immediately upgraded Scene.js to use Canvas 3D. And there's the very first test model, or maybe the second one after the cube, Goro shaded teapot. And so as hobbyists and experimenters came out with their Canvas 3D experiments, people were looking at that and just going, wow, is it actually running in the browser? Is that an animated GIF? Oh, no, I can actually interact with that. I can rotate that. And so desktop graphics programmers were a little bit surprised because, the browser was not really taken very seriously. And the largest graphics software companies started considering their options. And everyone knew that the web was going to take over everything, but now the big companies are actually thinking it's now going to happen, and we can put our products on the web. And also at the same time, the graphics gurus started exploring WebGL and posting their implementations of classic algorithms that run in the browser. And so CTOs and CEOs of companies were, their first problem was, there's no libraries. There's not many libraries out there built on top of WebGL, and we don't want to program on the bare WebGL metal, so what is available? And around 2009, 3JS was not yet using WebGL, and so there was a gap in the market. And so I quit my Java job and devoted myself to developing Scene.js. And yeah. So in 2010, BioDigital decided to move their product from C++ and Open Scene Graph into the web so that people could use it anywhere. And so our mission in building a proof of concept for BioDigital Human was to make a version of the human that ran anywhere. And so in our first proof of concept, we took a collada model of a skeleton exported from Maya and loaded it into Scene.js. And it took 2 minutes to load, and it rendered it around 10 to 15 frames per second, which exceeded our expectations. And at this time, WebGL was still very glitchy in a lot of browsers. And yeah, there were many learnings from actually using Scene.js in production. It started as a joke, and then it ended up powering people's applications. And so their first requirement is to load those models really quickly. And so, of course, parsing collada in the browser was not so cool. So we built an asset server which would parse the collada and load the assets into the server, and then they would be downloaded into the client through a WebSocket. We're greatly inspired by Googlebody, which is now called ZygoteBody. That's still live, and it was created by Wan Chun as his 20% Friday project. And from that, we learned how to quantize geometry and that sort of thing. So, of course, one of their requirements is to navigate models fluidly. And so for this, in Scene.js, we applied the classic techniques of minimizing state changes. I won't go too deeply into that. I was very much inspired by OpenSceneGraph.js, which is a JavaScript port of OpenSceneGraph, which now powers Sketchfab. And then we continue to extend Scene.js with the features they needed to render their library of Maya-authored models. Around 2011, Microsoft was a little bit glitchy. And they, in context, published their security report in which WebGL was considered to be a security vulnerability. But yeah, now Microsoft are fully behind WebGL. In 2015, we wrote our first BIM application on Scene.js, and this was BIM Surfer version 1. And so BIM Surfer is a WebGL-based client application running on the front of BIM Server, to which you upload your IFC files, and the client will pull down on demand the geometries through a binary WebSocket. So more learnings from this. Scene.js attempts to wrap the functionality-oriented API of WebGL in a logically-oriented API, which is human-readable and intuitive, so that you don't have to get into the details of how WebGL works. However, it creates many layers, and it's very difficult to extend, and it doesn't scale well. You know, it creates a lot of, uses a lot of memory, uses a lot of garbage collection going on there. And we always found that we needed to build a layer of sort of business objects on top of it to adapt it to viewing engineering models. Also, I found that putting lots of training wheels and defaults into the framework was very good for getting people to use it, but it became a real pain for once people had learned how to use it. So the next evolution on top of Scene.js was Xeokit. Starting again, just looking at the code smells in Scene.js and reworking things. This time I abandoned the JSON scene definition and went straight for classes, components, and a classic scene graph architecture, MIT license. And then we built BIM Data Viewer version 1 on Xeokit. But now we're up against IFC models with hundreds of thousands of objects, and it's really hitting the limit here, because, yeah. And so this, so we had really big apartment models. What happened? Oh, yeah. Rendering 300,000 objects at 10 frames a second was not acceptable, and although we used geometry batching and instancing and things like that, it still wasn't scaling. So then I started Xeokit, so objectives, faster rendering, easier to extend, and a lower memory footprint, and also supporting double precision geometry, which is really important for BIM to support global coordinate systems, to be able to view a model at its original site placement in global coordinates in the browser. So Xeokit emulates double precision rendering, and also a GPL license for sustainability. So in 2020, I partnered with Creoox, and yeah. So right now, Xeokit is one of the very few libraries that support double precision and global coordinates, and those are really important because it means that you don't have to center your model. You can load a point cloud and an IFC model alongside each other, and if they're both in the same global coordinate system, they just automatically register with one another. Yeah, we also use some mesh batching technique, which I'm not going to go too deeply into here. So here's the problem with global coordinates on WebGL or in most GPUs, which are, I think, accurate to something like 7 decimal places. And as the numbers get really big, the available values on the floating point scale become more sparse, and so it rounds to the nearest value. And so what we've got here is an apartment in Lyon, France, and it's in its real world coordinates, and there they are rounding. And in Xeokit, we use a tiled coordinate system like Cesium.js. Automatically, it's transparently just splits things into tiles. And so we're able to emulate 64-bit precision on single precision GPUs. Also, we have our own binary native format to which we convert various AEC file formats. It's similar to Autodesk Forge's derivative format conceptually. And it compresses geometries, quantizes and opt-in codes, position coordinates and normals. And yeah, we're able to get a pretty small memory footprint. And we also store the geometry in GPU on textures. So we use data textures to store the geometry and the visual states of meshes. And I won't go too deeply into that. Another differentiator is we have snap to primitive, which is really essential for making accurate measurements. And this was contributed by Tony Marty at Trivia G, which I've misspelled, sorry. Another differentiator, an integrated semantic data model. We can load IFC semantic models alongside geometry to classify the objects and create things like the explorer tree on the left there. We also, we can view federated models, and when we convert IFC to Xeokit's XKT format, the converters will split the models into lots of smaller XKT files. And that's really useful for loading big models in the browser because after loading each chunk, the browser has time to recover, and do garbage collection. And so we're able to load quite large models like the Baku Stadium here, which is, I think, about 1 gigabyte or something in IFC form. And that's everything. Hope that made sense. Any questions? Oh, hang on a sec, Damon. Here comes the mic.
So first of all, great presentation. Thank you for being someone that's been passionate about Web3D as well. Yet I'm curious, because as someone that equally has been back in the day since Vermal, it frustrates me to see that most web developers don't even think of Web3D, right? And so how do you think, why do you think that is, right? Why do you think that most web developers, they might have heard of Three.js, or they might have heard of some of these, but why do you feel there's that massive disconnect, right? I mean, this has been for over a decade running natively in the browser.
I wasn't really aware of a distance. I actually had the impression that most web developers quite enjoyed working with 3D when they had the opportunity.
But I think most of them don't even, that's the problem, is like they don't even know. The ones that are exposed to it, when I share with them, oh, this is Three.js or something like that, they get excited and they're like, oh, wow. But most developers are just still stuck in flatland. So I'm just kind of curious, as someone that's been in the space for a while.
Well, I think that prior to WebGL, the bar for 3D graphics programming was quite high. You know, you needed to have, typically you had a PhD or a master's in computer graphics, and like somebody like me, I'm a bachelor's degree, and I never thought that I would ever program in computer graphics. It seemed like a specialty topic that I really needed a postgrad degree to even dare to dabble in, and so I think WebGL has just sort of put it in the hands of a lot of people, democratized it, but I think a lot of developers see it as a very exotic sport. Oh, I don't want to get too involved in that, it looks too complex. But that's not really true. It's become a lot more accessible. I think it just has the illusion of being sort of exotic, elite kind of programming, perhaps. Yeah.
Thanks.
Any other questions?
Hi, Lindsay.
Hello. Hi.
Can you say a few words about the roadmap for the next years? I know this was just going backwards, but what about future?
Yeah, right. So I didn't want to include it in this presentation, but we're working on Xeokit version 3. And so in this version, it's just a complete rewrite based on the code smells found in the current version. That's how we are at Creoox. We're constantly evolving. You know, we never sit with a static product. And so in Xeokit version 3, it will be natively TypeScript. It's a monorepo where everything is split into components, each in their own package. It'll have a pluggable, it's actually working at the moment, but it's not yet released. It has a pluggable renderer, so we can plug a WebGL renderer or a WebGPU renderer into it. Yeah, it's got a semantic data model, which is more powerful. It's an entity relation model. It's faster. It's just the code less code smells.
Yeah, thanks. I know we talked about this yesterday, but I thought other people might be interested to hear that you're going to have a big publish next year. Yeah.
Yeah, we'll publish it next year.
Yeah, great. Thanks.
Yeah. Very good. Okay.